Okay, now that we've looked at water and we've determined that it is a polar molecule with polar bonds, now I'm going to walk you step by step with carbon dioxide, CO2. So the first thing you want to determine is whether the substance is ionic or covalent. You're going to look for a metal or ammonium, that's NH4+, with some other negative ion, so like ammonium chloride. If you have ammonium or a metal, then it's ionic. Carbon dioxide does not, so therefore carbon dioxide is some sort of covalent compound. What type is it? It's either going to be polar covalent or nonpolar covalent. Polar ionic does not exist. Nonpolar ionic does not exist. Be careful with that. If your molecule is covalent, you need to draw it. So that's what we're going to do next. We're going to draw CO2. Carbon goes in the middle. Carbon always goes in the middle. And it's a good idea to start with your outer on your outer first. So oxygen has a Roman numeral 6 above it, so it has 6 dots. Carbon has a Roman numeral 4 above it, or 14, so it has, I'm going to give it 4 X's. Okay. Now, when you look at carbon, you'll see that it only has 4 valence electrons around it. And so then you need to ask yourself, can carbon have less than 8? Is it part of Balbi? Only these 3 elements can have less than 8. And carbon is not part of Balbi. Then you need to ask yourself, is it part of CNOF? Carbon, nitrogen, oxygen, and fluorine. Clearly, this is part of CNOF, and so it has to have exactly 8, no more, no less. So in this case, I don't have enough valence electrons for an octet. And if you'll remember, if you don't have enough, try a double bond, try a triple bond. If you have leftovers, if you have too many, do a lone pair loop. We don't have leftovers, we don't have enough. So I'm going to take 2 of my electrons and I'm going to move them to the inside. Okay, that now does give this oxygen 8, and it gives the carbon more. It now has 6, but carbon still doesn't have enough. So let me bring another pair to the inside. Just remember, the goal is to get 8 for everything, especially for carbon and oxygen. They have to have 8. So with 2 double bonds, I can see that I have 8 for each of my elements. I don't want to go beyond 8 because carbon can't have an expanded octet. And then another little tip that will help you, carbon never has lone pairs, and it always has 4 dashes off of it. Okay, and so that's a nice, quick, easy way to determine that carbon's going to have 2 double bonds. All right, so once I have my structure drawn, the next thing I want to do is label my electronegativities. And when I have it drawn, I need to make sure that I have it drawn to its correct shape. CO2, I have 2 double bonds. And just remember, when you're counting up your domains, a double bond only counts as 1 domain. So each double bond is only 1 domain. This is 1 domain, and this is 1 domain. Okay, so we have 2 double bonds. We have 0 lone pairs. And so therefore I have 2 domains. 2 domains, it's linear. And that's what I'm showing here. I'm showing a linear structure. Okay, once I have it drawn to its correct shape, then I'm going to put in my electronegativity numbers. And then if I were to subtract right here, doesn't matter if it's a single bond, double bond, you're going to subtract your electron negativity numbers the same way. And then remember, it's the absolute value. So if I look at a carbon double bonded to oxygen, my electron negativity, my delta En, is 0.89. That's greater than or equal to 0.4. So that means this is a polar covalent bond. Be careful. I'm not saying polar covalent molecule. I'm saying polar covalent bond. How do I know if it's a polar covalent molecule? Well, if I look at this bond, I can see that the oxygen pulls on the electrons more. And if I look at this bond, I can see the oxygen pulls on the electrons more. So both of these oxygen are pulling electrons to the outside, and the higher electronegativity number has the negative charge. So the negatives are on the outside, the positive is on the inside. Higher numbers are the negative, lower numbers are the positive. So then, do I have a molecule that has higher numbers on one side than the other? No. The outside of the CO2, these are both negative. I don't have one side with higher numbers than the other. And so because this is a symmetrical molecule, it's going to be nonpolar. And nonpolar is a type of covalent. So even though carbon dioxide has polar covalent bonds, it's a nonpolar covalent molecule due to its symmetrical shape. Okay, so that was a long way. There are 3 things that you can look for to help you determine if you're looking at a polar molecule. And these are on your tips that I gave you. The first thing you want to look for are lone pairs on the central atom. So if your central atom has lone pairs, then it's going to be a polar molecule. The second thing you want to look for are elements that are different around the central atom. So different from each other around the central atom. And the third thing you can look for are only 2 atoms, not elements, atoms. So only 2 atoms that are of different elements. If you see any of these 3 criteria, then you know that you have a polar covalent molecule. Because these are nice, easy ways to determine that it's polar, it's not a bad idea to memorize these 3 things. Okay, so that's part 1 of your notes on polarity.